We are in geometry. We are on lesson 1-15. There are too many people talking. I don't want to take away HP, but I will. Everyone has been officially warned. If you are talking out of turn when you should not be talking, you will lose HP. So, rotations, reflections, symmetry, 1-15. It's a conceptual day, less work to actually do, more conceptual. Let's talk about some vocab. Regular polygon. You've heard this before, maybe briefly. I'm formally defining it now. All sides are congruent. And all angles are also congruent. When you think of a... Are we talking out of turn, Jaden? Is that what
Sorry, I was asking for a pencil.
Okay. When I see a hexagon in my mind's eye, when I think about a hexagon, you usually are thinking about a regular hexagon. If I think about a quadrilateral, a regular quadrilateral would be a square. Here is a really bad example of a hexagon. 1, 2, 3, 4, 5, 6. Obviously, none of these sides are really equal. This side is clearly not equal to that side. This is not a regular polygon because none of the sides are really congruent. If all the sides are congruent, like this hexagon right here, that is a regular polygon or a regular hexagon. All right. So we'll be seeing that in the future, but let's go ahead and talk about our symmetry. So we know what a line of reflection is, a line of symmetry. So this is called just line symmetry. There's 3 types of symmetry that we're going to hit today. Line symmetry, we're going to have rotation symmetry, and identity symmetry. Each of those 3 types we need to have mastered. So line symmetry. If you fold a shape on its line of symmetry, think about folding a piece of paper. If you fold it on its line of symmetry, then then both sides line up. What's going on, Leo? Looking for a pencil?
Yeah.
Do you want to borrow one?
He takes HP. No.
Then you need to be in your seat and ask for someone else to give you a pencil. Just take this pencil.
I don't want to lose HP. I'll just be in my seat.
No, you need to take notes. Take notes. All right. Both sides line up. And a more formal definition is that when I fold across the line of symmetry, the pre-image and image line up. All right. I'm just going to do my informal definition because I think more people will remember it. They just line up. Here's an example. I want to find all of the lines of symmetry in these 4 shapes. I'll give you the first one. I'm just going to choose a random one. Oh, look, there's a hexagon. If I decide to draw a line right here, boink, that's a line of symmetry because if I fold across that line, then both of the sides line up. Here's another one. Ready? Boink. Find all of the lines of symmetry in all of these 4 shapes. Maybe they have some, maybe they don't have some. That's kind of our question. Do all shapes have a line of symmetry? Draw as many as you can find. I'm going to be walking around and seeing what you guys write. All right, so what we should have got, here's your answer key. This right triangle has no lines of symmetry. This is not a line of symmetry. I can't cut it in half that way. There's no lines of symmetry. This rectangle has exactly 2 lines of symmetry through the center there and through the center there. There are the 2 lines of symmetry. There are no lines of symmetry across the diagonals. Make sure you did not put those. If you want to see why that's the case, then go ahead and fold a piece of paper, an 8.5 by 11 piece of paper across the diagonals. You'll see that it doesn't quite match up. A hexagon has a ton of lines of symmetry. Let me see if I can draw all of them. It goes through all of the vertices. Let me move this. I'll fix that one in a sec. Looks like this and this. Let me move this one to its correct spot. Move this one to its correct spot. All right, there are all the lines of symmetry on a hexagon, a regular hexagon. There are a ton of them. I think there's a total of 6 of them. And we talked about the parallelogram informally off camera, which was you can't ever have a line of symmetry in a parallelogram. Many people think, oh yeah, you can draw one maybe like that, doesn't quite work, maybe like that, doesn't quite work, like that, or like, I don't know, something else. There are no lines of symmetry for a parallelogram. So that's all we got. So we'll say none here and none here. Write that down in your notes. Make sure you have all the lines of symmetry and talk about which ones don't have lines of symmetry. This is probably one of the coolest properties you'll see this week, and this one baffles my mind still. So let me go ahead and open up Geogebra. So multiple reflections. So if this is my starting image in the top left, let's see what happens when we reflect multiple times. Geogebra, go faster, please. All right, so check this out. All you're doing is sitting back, relaxing, and paying attention, Jaden. Yep, you're sitting back and paying attention. So check out what happens. I'm going to reflect this shape across this line just by clicking. I just reflected it. We can see how that's reflected, nod our heads. Yes, we see that's a reflection. Check out what happens when I reflect this shape across this line. Those two, do you see that they're reflected?
Yeah.
But check out the original shape versus that second image, the pre-image and the second image. What does it look like happened? A rotation. And check that out also. So if I undo both of those and I decide to do a rotation of this point around L, and I rotate by, I don't know, A degrees clockwise, you can see that it eventually does go right to that reflection. In fact, if I come back here and reflect around the line, this reflected here, this reflected here, it gets me to that shape if I come back here and make A approximately, yeah, right there. Two reflections is the same thing as a rotation. Isn't that crazy? I don't know. It blew my mind the first time I saw that. Maybe it's blown your mind. Maybe I'm taking away from that. But this is what I want to write for the notes. Two reflections. Right here. This was a reflection right there. A reflection right there. Do your little arrows so you can see where you started. This was your pre-image, image, and then second image. Is the same thing, is equal to one rotation. This one was rotated around down like this. And the coolest part yet is that the point or the center of rotation is where those two lines of reflection intersect. This line and this line intersected at this point. I call that point L on Geogebra. This point is the center of rotation. So to find the center of rotation, look at the lines of symmetry, which we just talked about. Where those lines of symmetry meet is the center of rotation. I can now find the center of rotation of this object and this object because I see where all those lines intersect. But now my question for you is, do these two shapes have a center of rotation? And to do that, we need to formally, or at least informally, define what a rotation symmetry is. But reflecting twice across different lines is the same as rotating. Chewy, what's going on? Okay. Rotating around the intersection of those lines. Kind of a cool property. Hopefully you can remember that where those two lines intersect, two reflections equal rotation. The rotation is around the intersection point. Try to remember that. And we're going on to the next part. Rotation symmetry. We're going to informally define this. When you rotate a shape around its center of rotation, and it looks the same. And I'm going to put a note here. Zero is less than theta, which is less than 360 degrees. So a rotation symmetry is whenever you rotate by bigger than 0 degrees, by less than 360 degrees, and it looks the same, that means you have found a symmetry of rotation. For example, if I looked at my hexagon, if I were to rotate 60 degrees, this hexagon would rotate onto itself. I guess I really need to show you an example. Do I have an example down here? Not quite. Let's see if I can make one really quick with Geogebra. So, check out this regular hexagon. Regular polygon. Boom, boom. I'm going to go with the hexagon, 6. Now, by moving this hexagon here, I can rotate this hexagon. So let me go ahead and find the center of rotation by making a line. The way that you find the center of rotation is by connecting your lines of symmetry. The intersection point right here is going to be the center of rotation. So if I decide to rotate around a point, hold on, let me get my slider set up. Let's say A is between 0 and 360. If I decide to rotate this shape around point G by A degrees clockwise, look at what happens when A gets to 60. So I'm rotating, 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 boom. When I get to exactly 60, and let me maybe, once it's exactly 60, it goes back to itself. When I go another 60 degrees to 120, it goes back to itself. When I go another 60, when I go to 180, it rotates back to itself. Ooh, too far. When I go another 60, it rotates back to itself. So those are all rotational symmetries. When you rotate around its center and you rotate more than 0 degrees, less than 360 degrees, and it looks the same, that is a rotational symmetry. All right, and we know this already. I've talked about this before. The center of rotation is the intersection of the, who wants to do this one? Lines of symmetry, yeah. One you'll learn all day. If you rotate by 0 degrees or 360 degrees. So it's the same shape. It's technically a subclass of rotational symmetry, but yeah, you're basically not rotating it or rotating it so that you come back to itself. That's called the identity symmetry. Every single shape will have the identity symmetry. So in the homework, I'll show you the homework right now. In the homework, it asks for what types of symmetries are there. Every single answer will at least include the identity symmetry because the identity symmetry is in all things. All right, so let's try example 3. We know how to do this one already because it's a simpler shape. Go ahead and draw all the lines of symmetry. You know how to do lines of symmetry. You've done that before. Go ahead and start drawing the lines of symmetry. Here's one of them, from A to C. Draw the rest of them. All right, so what you should have drawn is diagonals through each of the corners and through the center like this and this. Hopefully all the lines actually matched up in the center. I'm going to make a giant point. That way it looks like that actually happened. All of those intersections are the center of rotation. And what I have realized, sadly, too late, is that if there are no lines of symmetry, then there is no center. Well, there's no way to construct a center of rotation from this lesson. So for this one, you can't do it. I mean, it exists, but we can't do it yet. This one exists, but we can't do it yet. So you can just cross both of those out. We'll eventually learn how to do that. I just realized that it's not this lesson. Sorry about that. So go ahead and talk to me. How many symmetries were there? Count all of them. How many of these reflections do we have? Did you count them up? Hold up the number on your fingers. Nice, you all got it. It's 4. Here's the harder part, in our last part of our lesson. How many rotational symmetries were there? And because technically the identity symmetry is a part of rotational symmetry, count the identity symmetry in your count. How many rotational symmetries are there? Should I show you how to do this? You want a hint? Let's assume that we always start with vertex A. Vertex A, if I rotate it by 90 degrees, I'll get to B. A can go to B. That's 1. So A to B, I can write up here, A to B, that's 1. A goes to, what's another one? A can go to C. I heard Leo say A can go to D. Is there any other one that I can go to? A can go to A. That's the trivial one that's called the identity symmetry. This one is the identity here. We do a capital I for identity. Are there any other possibilities? Say again, C. A goes to C. Is that what you're talking about? Or C goes?
Like A can rotate.
Yep. Yeah. So that's this one here. Perfect. Yeah. So there are only 4 of them. All 4 of them. So again, 4. And that's it. All right. So just because it doesn't have lines of reflection doesn't necessarily mean it doesn't have a center of rotation. In fact, every single one of these has a center of rotation, but to find it is a little bit harder. So what I want in your summary, I guess technically this guy is incorrect. We want lines of symmetry intersect to make the center of rotation, which is essentially saying the same thing as reflecting twice across different lines is the same as rotating around that intersection of those lines. Those 2 things I want in your summary. You can add other things as well. Go ahead and write that now. Both of the stars. Write both the stars in your summary.